Hello everyone, and welcome to this Getting Started tutorial for fluid solid heat transfer simulations using Ansys Discovery. This is also commonly called a conjugate heat transfer simulation. Let's go ahead and get started. If this is your first time using Discovery, please be sure to review all the slides on the welcome screen, as there is a lot of great information that will help you get acclimated with using the tool. At the end, you can go ahead and start an interactive tour on a variety of different topics, or you can open our homepage by clicking this button or the X in the top right corner. On our homepage, you have the ability to access some recently utilized files as well as our samples. But in our case, we want to open a new geometry. So let's go ahead and navigate up to Browse, where we can select this arrow to expose our dropdown, where we can choose to open a geometry file. From here, navigate to the appropriate file location, choose your file, and select Open. By default, the geometry is loaded into our Explore mode, which utilizes our live GPU-based solver. As with the 2022 R1 release, conjugate heat transfer simulations can be completed in both our Explore and our Refine modes. Part 1 of the series will be dedicated exclusively to utilizing our Explore mode, so let's go ahead and dive on in. Before setting up our physics boundary conditions, it's always important to review the geometry that was imported. In the top left corner of this window, you can see our geometry tree. In this case, the top level is this IGBT cooling. Underneath, we have three subcomponents for each of the IGBTs that are sitting atop of this base plate. On the base plate, you can see that we have an internal cooling channel, but in its opaque state, it's a little bit difficult to see the path that the fluid will take. So let's go ahead and make this body transparent. This can be done by left-clicking to select a face on the geometry. Then you can navigate down to the bottom left corner of your environment to the view arc, where you can select this icon here to make the body transparent. Let's go ahead and click an empty space to remove our active selection. Next, let's rotate our geometry so that we can better understand the path that the fluid will take. You can do this by simply clicking and holding your middle mouse wheel button and moving your mouse. This gives us a much better understanding of the path that the fluid will take in our domain. Once we've done so, we're pretty much ready to begin to set up our simulation. But first, let's go ahead and navigate back to our home view. This can be done by going down to our view arc and selecting this icon here, or simply you can hit H on your keyboard, which is our keyboard shortcut for the home view. Taking a quick look up into our IGBT cooling geometry tree here, you'll notice that we only have the solid bodies modeled. But for a conjugate heat transfer simulation, we need to have a body for our fluid region. This can be done natively in our Discovery environment utilizing our volume extraction tool. The volume extraction tool is available on our Prepare tab, so let's go to the top of our window and choose this Prepare tab here. Next, we can navigate down a little bit and select our volume extraction tool here, which will create an enclosed volume based on our bounded region. So let's go ahead and click this icon here, which will open up our heads-up display. If we take a look at our tooltip down in the bottom left, it's asking us to select the faces that enclose the fluid region. In our case, we want to select this face as it is both complementary to our inlet and outlet. Next, we need to select an internal face to define as our seed face. So let's go ahead and select our seed face filter and then select the internal diameter. From here, we can click this check mark or hit enter to confirm. This will complete our volume extraction process, so let's go ahead and click this now. As you can see, our volume extraction went successfully, so we can go ahead and close our heads-up display for our volume extraction tool by hitting escape 2 times. Let's go ahead and dive into setting up some of our physics boundary conditions, and we can do so by starting and navigating to the top of our environment and selecting our simulation tab. In Discovery, there are 2 different ways in which you can apply physics boundary conditions, and I'll go ahead and show you the 2 ways now. The first way is to utilize our ribbon-based controls. Let's go ahead and do this to define our inlet conditions. So let's go ahead and navigate to the top, select our drop-down where we can choose our flow condition. This allows us to define an inlet or an outlet in our domain. So let's go ahead and simply select this face as our inlet here. You can see that the yellow arrow is indicating the direction of the flow. As soon as I select my face, as you can see it turns orange, the right side of my heads-up display appears, asking for numerical input to define this inlet. As you can see, we can define it as a velocity, a mass flow rate, pressure, or a swirling flow. For the sake of example, let's choose a mass flow rate of 0.1 kg per second. Now to accept this, we can click this check mark here or hit enter on my keyboard. So let's go ahead and click this check mark. Now for our application, we're going to be using this flow to cool our IGBTs, so it's important for us to define a temperature to this flow. This can be done by navigating to the right side of our heads-up display and clicking this thermometer icon here. This will provide us with another text box which we can edit our value. And in this case, rather than 22 degrees Celsius, let's simply enter 10 degrees and hit enter on our keyboard to confirm. As you can see, this is now updated in our tree based on our updated value. Let's go ahead and hit escape 2 times and let's define our outlet. The secondary way in which you can apply physics boundary conditions in Discovery is by first selecting the geometry. Now you'll notice that this hex will follow us around the environment. Clicking the hex will open up our halo. By default, we are in our physics halo because we're setting up a physics simulation, so this allows us to apply physics boundary conditions. However, we have different modes to our halo. As you can see, I can select this icon here to have some advanced selection options, and I can select this cube to change my halo to modeling controls. But let's go back to our physics view, go up to the top into our fluid flow halo, and select our fluid flow icon. From here, you can see that we have our default conditions, or the ones that were used previously, as our conditions now. But we want to change this to an outlet, so on the left side of our heads-up display, let's simply click this drop down here and choose outlet. Next, let's click this check mark to confirm, and once it is added to our tree, we can simply hit escape 2 times to close our heads-up display. Before applying our solid thermal conditions, let's go ahead and review what we've created so far. On the left side of our screen, we can see our physics tree, which is composed of our material definitions, and in this case, we're using water to cool our IGBTs in the cooling channel, which is an appropriate assumption. And below this, you can see our inlet and outlet conditions that we created. Down in the bottom center of our screen, you can see our simulation information display, which is this large hex in the center. This provides us with a brief amount of information of what's going on in our application. This icon in the center means we are solving a fluid thermal simulation purely on our flow domain. If you hover over this icon, you can see that it highlights just our fluid region, and this is just a fluid-only simulation. We are not including the effects of any solid components. This can also be mirrored up in our geometry tree, where you can see we have toggle switches for both our suppression and activation for physics, as well as our visibility here. As you can see, only our fluid volume is included in the simulation. Next, let's go ahead and define our solid thermal applications before we go ahead and close for part 1. To apply our solid thermal conditions, let's go ahead and utilize our ribbon this time. But let's go ahead and select our geometry first. So I'm going to go ahead and triple click here to select this CAD body here. So 1, 2, 3, and it allows me to select a body. Let's go ahead up to our ribbon this time, and let's go ahead and grab a heat condition. This allows us to define a total heat or a heat flow into this environment. For this example, I want to use 200 watts on each IGBT. So let's go ahead and hit 200 and hit enter. Let's go ahead and repeat this process for the last 2 remaining IGBTs. Once again, we're going to triple click to select the entire body. And as you can see, it's remembering our last numerical input, so we can simply hit enter. And once again, I'm going to triple click this body to select the entire source and hit enter once again. Let's hit escape 2 times to close our heads-up display before we review our applications. Now, if we take a look on the left side of our screen, rather than just fluid flow boundary conditions, we have 2 different groups. As you can see, we have a solid thermal group as well as a fluid flow group. The solid thermal group consists of our heat flows that we created as well as a convection coefficient. This is created by default on all surfaces that do not have a thermal condition. Below this, you can see our fluid flow group, which includes our inlet and our outlet. Below this, you can see our connections. These connections are between our solid entities, and simply these are the areas where we're going to have conduction. Below our connections, we have our fluid-solid interfaces, which were created by default. This is allowing the physics to transfer between our fluid and our solid domains, and you can see the path that it will take. Additionally, you can now see in our simulation information display that we have 2 icons showing. If I hover over the first one, this is going to highlight our fluid thermal region, in this case just our flow domain. And if I hover over our thermometer now, this will highlight all of our solid components, indicating that this is where our solid thermal region will be solved. Thank you for watching part 1 of this Getting Started tutorial for fluid solid heat transfer simulation. Please be sure to tune into part 2 and part 3 as we will cover more information. Thank you very much and take care.